Hey, this is Emily, and this week's module is all about probability. It's an introduction to basics in probability and how probability relates to our work in statistics. So let's talk about how probability impacts our everyday lives. Probability allows us to predict the likelihood of an event occurring, and we plan our lives around these probabilities. So, one example of probability in our everyday lives includes the weather. So, we all know that meteorologists tell us each day the likelihood that it will rain, that it will be sunny, that it'll snow. But we use those probabilities to make choices about how we'll spend our time. Like this morning, I saw that it was a 90% chance of rain, so I said that's pretty likely it's going to rain. I'll go to the gym instead of going for a run. Now, it wasn't 100% certain that it was going to rain, but I used that as a best guess and decided I'd rather not take the risk of getting caught in the rain. We use probability to think about macro level events too. This is the cone of uncertainty that the meteorologists and statisticians at NOAA and the National Hurricane Center put together and use to inform the public about the likely direction of a hurricane over time. This is actually grounded in statistical principles to tell us about the predicted future direction of a hurricane. So how this is constructed is that the base of the cone starts at the known current point of the hurricane, and then meteorologists use statistical tests and they design a cone that includes the future probability of the direction of the hurricane, and it's generated to be right about 66% of the time. This is a way to help us make good decisions and plan for an emergency. If we wanted to be 100% certain about the direction of a hurricane, we'd have to include all of the very unlikely directions that the hurricane might go. But if we were preparing for every unlikely event, we would be stuck and unable to make any decision at all. And what we need to remember is that probability is what helps us make decisions about the future. If we had to account for every last possible probability, and we wanted to be 100% certain of the direction of the hurricane, we'd have to include the very unlikely probability that it would move in directions that are not indicated on the cone. Even the very small probability that it would go backwards. We would have to draw a cone that was basically a full circle to encompass every possible probability. But when we're making big decisions, we don't need to be 100% certain of what will happen. We just want to know what's most likely. So again, this cone is developed around a 60 to 70% likelihood that the hurricane will move in a particular direction, so that the general public knows how to plan for the emergency. Probability is a big part of our political lives as well. Political polls are conducted all the time to predict the likelihood of political events, such as the likelihood that a given candidate will win an election, that a legislative measure will pass, that a particular ballot initiative will pass. Now, sometimes these are not always correct. We will learn about statistical error later in this course, and statistical error is important and expected. If you're interested on what's happening in the political sphere with latest polling, I encourage you to check out this website, projects.538.com/polls, and you can track what statisticians are doing to understand their polling of the general public to determine future political events. Sports is another arena in which statistics plays an important role. Players' records of success in previous games are used by statisticians to predict their success in future games. Even lineups are structured by coaches around probabilities. And there's been a lot of pushback in the sports world about Major League sports becoming a game of statistics instead of athletics, like Statsketball instead of basketball. Although it's really fascinating what even young statisticians can do. These are the results of high school and college students in a March Madness contest that was run by the American Statistical Association. And what they did was start out with draft points to spend, built statistical models spending those points on different team picks. The winning students developed cost efficiency ratings for the teams in the tournament, figuring out who to pick and how it would produce the most wins. Really interesting. Probability also plays a big role in the art and the science of practicing medicine. Physicians prescribe medicines based on the probability that they will cure a given ailment or treat a specific symptom. Thinking about an everyday example, consider prescribing trends in birth control. One of the main measures is the statistical probability that your birth control, when used, will be effective. And individuals and their doctors make decisions about what methods to use, in part based on those statistical probabilities. Now, there are, of course, many other options to consider, and I highly recommend this website called Bedsider, and you can visit their matrix here, bedsider.org/methods/matrix, to learn more about how different birth control methods stack up against each other with their statistical efficacy probability and other components to consider. So how do probability and statistics relate with one another? While probability attempts to predict the likelihood that something will occur, statistics examines events that have already occurred in an attempt to identify patterns. So while probability thinks about hypotheticals or the future, statistics looks at what already happened and tries to find patterns. For example, consider a jar of jelly beans. Someone investigating probability would start by first figuring out the proportion of each color, and then would ask the probability of drawing a red jelly bean. So if they knew that there were 100 jelly beans in the jar and that there were 10 red jelly beans, they would know that the probability of drawing out a red jelly bean would be 10%. Whereas a statistician would infer the proportion of red jelly beans by taking samples from the jar over and over, perhaps taking 10 jelly beans out of the jar, figuring out the distribution of colors, and making inferences and assumptions about the entire population of jelly beans inside that jar. So probability and statistics both look at the same information using different methods. Probability is key to our understanding of statistics. We're going to use probability in a few different ways. We're going to make inferences about the data throughout this course by using probability distributions. And we're going to use probability to predict the likelihood our outcome has occurred by random chance. An experiment is a planned operation carried out under controlled conditions. And no, it doesn't have to take place in a lab. For example, flipping one fair coin is an experiment. Now, if the result is not predetermined, then the experiment is said to be a chance experiment, that the results are by random chance. For example, if we flipped that one fair coin twice and we didn't do any sleight of hand tricks, or the coin wasn't weighted more on one side than the other, if we truly had a 50% probability of scoring heads or scoring tails, that's a chance experiment. Now, the result of an experiment is called an outcome, and you'll hear this word throughout the course. An outcome is just a result. And we call the sample space of an experiment the set of all of these possible outcomes, including everything that is a success and everything that's a failure. Now, an event is any combination of our outcomes. We'll go through examples, but first let's think about how probabilities are distributed mathematically. We consider probabilities to fall between 0 and 1 when we write them as proportions. And we consider it inclusive. So that means we include 0, we include 1, and then we include all numbers between these values. So if something was very unlikely to happen, it would be close to 0. But if we are certain that something will never happen, if it's impossible, it happens 0% of the time. Or if we wrote that as a proportion, that's 0.0. If we are absolutely certain something will happen, that it happens always, 100% of the time, we write that as a proportion as 1.0. Now, before I review further, let's talk about the way that I've written the probability of an event. P, the probability, parentheses, of event A, in parentheses. So this event is called event A, and I'm asking about the probability of event A happening. If the probability of event A happening is 0, it means that event A can never happen. It happens 0% of the time. If the probability of event A equals 1, it means that event A always happens. it happens 100% of the time. And if the probability of event A happening is 0.5, it means that the event A is equally likely to occur or not to occur. Equally likely means that each outcome of an experiment occurs with equal probability. We have a law of large numbers that operates as follows. If you take samples of larger and larger sizes from any population, then x bar, the mean of the sample, is likely to get closer and closer to mu, the mean of the population. Well, this applies to probability too. The law of large numbers in probability operates as follows. As the number of repetitions of an experiment is increased, the relative frequency obtained in the experiment tends to become closer and closer to the theoretical probability. Even though the outcomes do not happen according to any set pattern or order, overall, the long-term observed relative frequency will approach the theoretical probability. Let's think again about a random chance experiment of flipping a coin. Half of the time we expect to flip heads, and half of the time we expect to flip tails. The probability of flipping heads is 50%. Each time I flip a coin, the probability of flipping heads is 0.5 or 50%. However, if I flip heads, does that mean that I'm more likely to flip tails the next time? No, the theoretical probability of flipping heads always remains the same, 0.5 or 50% of the time. However, if I repeat this experiment over and over and over again, about half of the time I'll flip heads and about half of the time I'll flip tails. The probability distribution function is used to determine the probability distribution for discrete variables. If a variable is a discrete variable, its probability distribution is called a discrete probability distribution. Now, just as a reminder, when I'm talking about a distribution function, I'm talking about frequency. If I have a set number of events, how many times, what is the frequency that something is likely to occur? We can show that in a frequency table, or we can show a frequency distribution on a graph. Discrete variables are variables that can only take on a certain number of values. In other words, they don't have an infinite number of values. You can only roll heads or tails. There aren't other values. Or if you can only earn 0 to 10 points on a 10-point scale, that's a discrete variable. Continuous variables, on the other hand, are the opposite of discrete variables. They can take on an infinite number of possibilities. Think about the infinite body shapes that humans have. There are infinite combinations of height and weight measured to the smallest possible decimal. Weight and height are what we use to produce your BMI score. So there are infinite values for having a certain BMI, especially when you consider calculating to a very small decimal point. Let's think about a discrete probability distribution by using an example. Suppose you flip a coin 2 times. This simple statistical experiment can have 4 possible outcomes, and I'll review them here. You can have H, 2 heads. You can have H, T, 1 head, 1 tail. You can have T, H, that's 1 tail, 1 head. Or you can have T, T, 2 tails. Now, let the random variable x represent the number of heads that result from this experiment. The random variable x can only take on the values 0, 1, or 2, so it's a discrete random variable. In the first outcome, we have 2 heads. In the second outcome, we have 1 head. In the third outcome, we have 1 head. And in the final outcome, we have 0 heads. So, what is the probability that you will have 1 head in your chance experiment? Well, how many outcomes are there? There are 4, and 2 out of those 4 outcomes have 1 head in the set of 2 coin flips. So that means that 2 out of 4 times, or 50% of the time, we theoretically expect to have X, the number of heads, equal 1. What is the probability that you have 0 heads in your 2 coin flips? That's right, 25% of the time we would expect 0 heads because 1 out of our 4 outcomes has 0 heads. We can represent that information as a table or as a graph. I'll walk you through it. So as we saw on the previous slide, 25% of the time, here represented as a proportion, 0.25, 25% of the time we expect to have 0 heads. 50% of the time, or 2 out of the 4 possible outcomes, we expect to have 1 head, 1 tail. So that variable X, number of heads, would equal 1. And 25% of the time, we would expect that our outcome would have 2 heads. We can represent that graphically here. Now, this graph is set up so that the number of heads is here on the x-axis, and then the probability of getting that score is on the y-axis. I've plotted it out here. 25% of the time, or 0.25, represented as a proportion, we expect to have 0 heads. 50% of the time, or 2 out of the 4 outcomes, we would expect 1 head. And 25% of the time, we would expect both of our coins to be heads, or for us to have X equals 2 heads. Now, the above table and chart represent a discrete probability distribution because it relates each value of a discrete random variable with its probability of occurrence. I want to point this out now, and we're going to review it throughout the rest of this lecture. If we add up all of the probabilities that are possible in our experiment, it will equal 100. Do you believe me? 25% plus 50% is 75%, plus another 25%, that's 100%. Let's talk very quickly about one discrete probability distribution you'll encounter a lot in statistics, the binomial distribution. There are 3 characteristics of a binomial experiment. There are a fixed number of trials. That means we think of trials as repetitions of an experiment, and the letter N denotes the number of trials. There are only 2 possible outcomes called success and failure for each trial. The letter P denotes the probability of a success on one trial, and Q denotes the probability of failure on one trial. And all of those successes and failures, and all of those probabilities, the probability of success and the probability of failure added together, always equals 1, or 100%. The N trials are independent, and they're repeated using identical conditions. Because the N trials are independent, the outcome of one trial does not help in predicting the outcome of another trial. The outcomes of a binomial experiment fit a binomial probability distribution. The random variable X equals the number of successes obtained in the N independent trials. The mean mu and the variance, the standard deviation squared, for the binomial probability distribution are calculated as follows. The mean equals the number of trials multiplied by the probability of success. The variance is N, the number of trials, multiplied by P, the probability of success, multiplied by Q, the probability of failure. Standard deviation is the square root of variance. So if we wanted the standard deviation, we would just take the square root of N times P times Q. Let me do a very quick example. Let's say your chance of scoring a goal is 10%. So we would say the probability of success is P is 10%, or 0.10. What would be Q, the probability of failure? Not scoring a goal, you might do Q equals 0.9, because P plus Q always has to equal 1. So let's use an example to understand how P and Q relate to each other. We want to make sense of all possible outcomes in a probability experiment. If P is the probability of successes, then Q is the probability of failures. P and Q represent all possibilities, so the probabilities of P plus Q is always going to equal 1 or 100%. Let's use an example. If P equals the probability of pulling a specific drink from a cooler, Q would be drawing any drink except the one that you've named for P. Sometimes we refer to Q as P prime. So let's look at this cooler full of LaCroix. So let's say that we want the probability of event L, reaching our hand in without looking in this cooler and pulling out key lime LaCroix can. What is that probability? Well, the probability of event L, I have 4 key lime cans, and I have 9 cans total. The probability is 0.44. What is the probability of L prime? Grabbing anything except a key lime can. How many cans are not key lime? 1, 2, 3, 4, 5 divided by 9 possible cans. And when we do that math, so again, the probability of selecting lime and the probability of not selecting a lime can, add those together, and it's going to equal 1 or 100%. Now, most students don't believe me at this point in the course, but I want you to think about distributions as a curve, and that when we're calculating the probability, what we're really doing is calculating the area under the curve. The curve itself is called the probability density function, often abbreviated as PDF, and we use the symbol fx to represent the curve. Fx is the function that corresponds to the graph. We use the density function fx to draw the graph of the probability distribution. Then we take the area under the curve, which is given by a different function called the cumulative distribution function. We abbreviate that as CDF. The cumulative distribution function is used to evaluate probability as an area. So again, think about a frequency distribution as a curve. When we're looking for the probability, we're taking the area under that curve. Here are some things to note. For a continuous probability distribution, the outcomes are measured, not counted. The entire area under the curve and above the x-axis is equal to 1, 100%. Probability is found for the intervals of x values rather than for individual x values. The probability of your value being between C and D is the probability that the random variable x is in the interval between those values, C and D. The probability that x is greater than C but less than D is the area under the curve above the x-axis to the right of C and the left of D. However, the probability that x takes on any single individual value is 0. So if you wanted to find the probability that x equals C, it's going to be 0. The area below the curve above the x-axis and between x equals C and x equals C has no width and therefore has no area. The area equals 0. Since the probability is equal to the area, the probability is also 0. Because of that, the probability that x is greater than C and less than D is the same probability of x being greater than or equal to C and less than or equal to D, because probability is equal to area. In this class, we're generally going to be using what's called the normal distribution, that bell curve we've been talking about. It's the most commonly used probability distribution. Let me illustrate some of the points I talked about on the previous slide. I'm going to draw a normal distribution. Let's say we wanted to find out the probability that x equals 1. If I drew a straight line up to the curve from 1, and I wanted to take the area under the curve of that line, I know that it looks like I have a very small thickness of my line, but in math, we think of lines as having no area because they have no width. So imagine an infinitely skinny line here. We would not be able to take the area under the curve above x equals 1. So the probability of x equaling 1 will be 0. However, let's say we wanted to know the probability that x would fall between 0 and 2. That would mean that I would want to find points 0 and 2 on the line, draw up to the normal curve, and what I would want to do is mathematically figure out the area underneath the curve here. This space is the probability that x is greater than 0 and less than 2. In fact, it's also the same thing as saying the probability that x is greater than or equal to 0 and that x is less than or equal to 2. Now remember our probability number line? Make sure that you review this table. It's really helpful for translating words to specific fractions, decimals, and percents. If you want to calculate probability, follow the following steps. First, list all potential outcomes. So let's think about our event as flipping 3 coins. And we want to know how many heads to expect if we flip 3 coins as an event. First, we want to figure out all the possible outcomes of flipping 3 coins in a row. We've illustrated this in this table. I'll go through a few. One outcome could be that we have the first coin is heads, the second coin is heads, and the third coin is heads. So we would have 3 heads. The second outcome would be that the first coin is heads, the second coin is heads, but the third coin is tails. The third outcome would be that the first coin is heads, the second coin is tails, and the third coin is tails. So we only have 1 head. I'll continue through the rest of these. Now count the number of possible outcomes. On the previous slide, you saw that there were 8 possible outcomes of this experiment. Now count the number of favorable outcomes. So what if we decided a success or a favorable outcome as an outcome that included at least 2 heads? If you go back to the previous slide, that means that outcomes number 1, 2, 4, and 5 all have at least 2 heads. That means that there are 4 favorable outcomes. Now divide the number of favorable outcomes by the total number of outcomes. There were 4 favorable outcomes, and we divide that by 8 total outcomes. That means that 1/2 of the time, or a proportion of 0.5, or 50% of the time, you will pass your test. Your outcome will have at least 2 heads. That means if we repeat this experiment over and over, we expect that about 50% of the time, we'll have at least 2 heads in our outcome. If you want some more probability practice, I recommend this admittedly very dorky game located at math-play.com/probability-game.html. There are good examples in here that help test to make sure you're understanding the fundamentals of probability. Like one example, a basket has 5 apples, 10 oranges, and 5 bananas. What's the probability of pulling out an apple? So the first thing that we need to do is figure out how many outcomes there are. There are 20 fruits in this basket, so if we were pulling out 1, there are 20 possible outcomes. Now, what's the probability of pulling out an apple? Since there are 5 apples, that would be 5 favorable outcomes divided by 20 possible outcomes, which would be 25% of the time. So here are my top 3 takeaways from this video. Of course, they're not comprehensive. It's just to make sure we're all on the same page. I want you to review the law of large numbers and how this applies to probability too. Remember how this works. If you repeat an experiment over and over and over again, your outcomes will start to mirror the theoretical probability. But remember, just because you had an outcome on your previous experiment doesn't mean your future experiment probability will change. If you flipped a heads on your last coin toss, it doesn't mean you're more likely to flip tails the next time. Your probabilities stay the same in each experiment. I want you to begin thinking of probability as area and frequency distributions. If I asked you, what is the probability of flipping one or fewer heads in your 2-coin toss? What you would do is take this area, 0.5, plus this area, 0.25, and add it together. There's a 75% chance that you would flip 0 or 1 heads in our 2-coin flip experiment we talked about earlier. Finally, number 3, I want you to practice P and Q probabilities, or P and P prime probabilities, like we did working with our LaCroix game. All right, everyone, thanks so much, and see you in the next module.